Okej. Powitajmy gorąco kolejną prelegentkę, Kamila Szewczyk, Statistical Data Compression.
Hi, so I came here to talk to you about statistical data compression a little. So let's outline the goal of this presentation. First, I would like to explain how more or less the compression algorithms work. Then we'll be talking about the practice, right? So for instance, if you have a question, how do I compress a particular file that I have? You might ask them, I'll try to answer. We'll talk about some new ideas and how I try to contribute to Linux data compressors. So briefly about me. I won't be speaking this all out, so you may read yourself. I came here from a very faraway land. Yeah, I'm recognizable by some people from my OSS work and SOLang-related work. That's actually how the organizers of this conference found me on the internet. And by the way, that font is not Comic Sans. So we'll be talking about two main classes of algorithms, and the first class of algorithms is going to be impulsive algorithms. So they use a sliding window or a dictionary to find repeated substrings in the file. And thanks to that, we achieve something that's very desirable in compression, which is somewhat slow compression and very fast decompression. This is nice, for instance, for installer images, right? And for the decoders are often remarkably simple. For instance, the gzip decoder, I think, is under 200 lines of code in the mini inflate library. And we'll also talk about statistical models, which is the core thing about my presentation. So through various methods, we're going to predict incoming data. We'll build a probability distribution for the next symbol, and based on that, try to guess what comes next. So many of you might be familiar with those names, probably not those on the right, maybe except bzip. The Unix compress program is a little antiquated, so you might not know it either. And there are other programs that kind of defy classification this way, as they use both methods. So we'll talk about those later at some point. So how does your gzip or LZMA or XZ, hopefully not backdirt, work? We start with a preprocessing stage. So the preprocessing stage is a little underestimated. We'll talk about it in a second. But basically, we use a bunch of filters, like a delta filter, particularly useful for images, or an executable filter that helps us with future compression ratio by making data more structural. It'll come in a second as well. So here we have a real-world example reported by a Fedora maintainer who says that the compressed live image of Fedora 31 saves about 50 megabytes of the 1.7 gigabytes of compressed size. It's not that impressive. I mean, not really, but the filter is implemented in under 30 lines of C code, so it's virtually free. The next part is the actual string matching, right? The core of the algorithm that makes us save on the entropy. So this stage is somewhat complicated. There's a lot of algorithms for string search. You might be familiar with some of those if you've ever read grep source code. It's a somewhat complicated problem. We may employ various parsing strategies or various match finding strategies, but we'll not talk about this too much. So the last stage we're interested in is entropy coding. The application of this stage in a codec is not necessary. For instance, if you ever used LZ4 or LZO, you might have been somewhat impressed with how fast it is, right? And that comes in part from the fact that LZ4 has neither the first, neither the last stages. It hinges purely on the string matching. So it can also be somewhat elaborate, like for instance in LZMA or Brotli. So this is also one thing that makes LZMA sometimes perform better than the standard. Right, so as I said, impulsive codecs really like structured data. So what you see, this thing in the corner, it's called a Stanford bunny. It's an object file that was exported from somewhere. Probably if you export your Blender project to an object file, probably get something like that. So what does this object file contain? Well, it doesn't matter exactly what it contains. What we need to know is it's just a bunch of numbers, right? There are floating point numbers, and by virtue of being floating points, they have a different length. For instance, if I have 1/3, I will write it as 0.33333 and many other threes. But if I have a quarter, I can just write it at 0.25. So the data is not very structured. So what this program does, maybe you can understand it, but hopefully not. Perl is not a good language. What this program does is basically padding every number in this file to a fixed length. So this makes this program less of a text file and more of a, how to call it, a structured file. So it saves about 22 kilobytes on this very simple program when using LZMA. There are other methods. If you were willing to add another line, you could save up to, I think, 80 kilobytes. That's a few % of the compressed size improvement. Right, so now that we know some things about codecs, we can try to put them in bins. So Unix Compress was an old program, probably most of you haven't used it. It uses the LZ78 algorithm, which uses a dictionary. And the problem with this algorithm is that it's patented. It was patented for the longest time. It was patented by 2 companies, actually, both Unisys, I think, and IBM. And at some point, Unisys actually started demanding royalties for GIF files. That's why you've seen so many people campaigning against GIF files. So gzip, the one that you frequently use, was created as some sort of a replacement for this program. And we have bzip2, which uses Burrows-Wheeler Transform. It's one of those statistical codecs. It had a predecessor, right? The 2 here is for a reason, and the predecessor was sacked for the fact that it used proprietary, or rather patented, algorithms. So LZ4, as I said before, doesn't have entropy coding. That's its most distinguishing feature, really. LZMA is a very high-quality codec, actually, and offers great compression ratio. Probably the best out of all impulsive codecs that we use, practically. And we have the standard, which provides a slightly better trade-off. We have LRZip. That's also a Linux tool that very few people know about. So if you have a tar file, you probably shouldn't store backups as a tar file, but even if you do that, then you can deduplicate those like the standard backup suite. And that saves you quite a lot of space, actually. So LZ0 was a predecessor to LZ4. It has a slightly better CR compression ratio than LZ4, but it's not used that much nowadays. If I had to guess, it's probably the fact that it's GPL licensed. So if you want to compress LZ0 in your code, it becomes GPL. Then we have PAC. That's one of the more obscure ones. It's a Hooter Prize winning data compressor. The Hooter Prize is a prize for compressing all human knowledge. So the current results are probably like 15 megabytes of compressing the first 100 megabytes of Wikipedia. It's a very hardcore contest, and the compressor is very slow. It's the order of kilobytes per second. And then we have Brotli. Brotli is still an impulsive codec and has 2 significant features. A built-in dictionary, so it can compress small files very efficiently, and it uses context modeling alongside the impulsive algorithm. We'll talk about in a second. Then we have bzip3, which I happen to make. It uses both BUT and context modeling. PPMD is something that probably WinRAR stands will recognize, but it's also a PPM statistical codec. So we've talked a bit about the distinguishing features. So LRZip, for instance, takes its hash algorithm for rsync. That's another program that you should probably know. gzip is interesting in that it's probably the most plain and boring codec you'll ever see, in that there's no processing, there's only Huffman coding at the end. It supports some predefined Huffman trees, but in reality this feature is more or less never used. LZMA, on the other hand, is extremely advanced. I mean, I'm not sure if you've seen the Wikipedia page, but most people don't understand most of it, in that it describes arithmetic coding and a very complex modeling. Z standard is a kitchen sink codec, right? If you want to compress data nowadays and you want a reasonable trade-off, you always use the standard. In that it's just so versatile. Yeah, so you might have recognized some of those names and some of those algorithms. So that's what we use nowadays. But what's the topic of this talk, right? There is a glass ceiling to compression, right? If you want to benchmark a compressor, if you want to pick a compression algorithm, it doesn't really matter to you what method it uses, right? It only matters what performance does it have. And there's an inherent limit to how well Impulsive can compress, right? Because as I said, it duplicates data. So it puts in the file in position of the repeated data, where can it be found in the file, like the file offset, and how many bytes to copy from there. But for all intents and purposes, the offsets are pretty much random, right? So they don't really compress that well. So there's not much we can do after Impulsive has been executed. But on the other hand, best compression is usually not the point, right? I mean, you could compress a file very well, but if it takes 2 days to decode the file, then it's probably not a good algorithm for general use. There's some uses for symmetric algorithms, which take as much to compress as to decompress, which is usually way faster than impulsive compression. There are some use cases, but it's up to you what do you want to use. So statistical methods are symmetric, as I said. Decompression is as fast as compression. And the things that impulsive codecs can't exploit, we'll talk about on the next slide. So you might have heard of this proverb, right? And it's very easy for you to guess what the next word is going to be, right? So an impulsive codec will notice that the next word has occurred somewhere in the file, we don't know where, but it's going to encode it as a match, and the match is probably going to be a pair of an 8-bit number and a 16-bit offset, right? So that's 3 bytes, compresses the whole word to 3 bytes. But what if we had some sort of a program, right, that can guess what word comes next? And if such a program could guess based on the context, then it would have thought, oh well, I have seen this context already, and followed by those words, I've seen this word, right? So this is a very crude illustration of how PPM works. So here you have a window of seen characters and not seen characters. So this fixed size window is used by the predictor, which is in the bottom right corner. And the predictor somehow comes up with a prediction, and this prediction is used to decide what is the most likely continuation of what we've seen so far. So that's an actual benchmark. So we have N week 8, 100 megabytes of Wikipedia in English. So PPMD is 20 seconds, 200 megabytes, and 23 megabytes of output. And LZMA is actually 4 times slower, it takes 3 times more memory, and generates a larger file, right? It's a bad comparison, but the compression speed for PPMD is going to be like, again, 15 seconds, maybe 16. But for LZMA, it's going to be almost instant. So the practical overview is that, as I showed before, we predict the next byte based on the previous n bytes. And the larger the context, the better. So if there's no match in a larger context, right? Like what if we take the last 16 bytes and we decide, all right, I haven't seen anything like that before. Then what? So what happens is we drop down to a lower order context. So instead of that, we consider only the previous 8 bytes. But for this purpose, we have to tell the decoder to just drop down to a lower order context. And we have to emit something called an escape symbol. And escape symbols was the reason why nobody used this algorithm for decades and decades to come. But Dmitry Shkvarin has solved this issue with his PPMII algorithm, where he came up with a clever method of predicting the probability that we will not see this context before. So again, the reason why we don't use it nowadays is because of the memory latency. The memories are still pretty slow, not as slow as they used to be, but our CPUs have gotten faster, more importantly. So many decades ago, they could compete with impulsive codecs, but nowadays the relative memory latency has increased, so we have not seen much improvement in PPM in recent years. And it's often outperformed by its BWT-based codecs in speed and compression ratio. And there have been some advancements on compressing on the GPU or the CPU by performing the Burrows-Wheeler transform. So the Burrows-Wheeler transform is something that bzip2 uses. It's a somewhat magical algorithm, right? Because it's a free and invertible way to improve the performance of a low-order compressor, right? So how it works? We take a string. Sorry for the Wikipedia screenshot, but we take a string, and then we take all the suffixes of the string. And after we have all the suffixes, we sort them lexicographically. So what this basically implies is that strings followed by similar strings are clustered together. So instead of having like a normal file, we end up with a file which has a lot of repetition, like single character repetitions, which again helps low-order context compressors that we've seen here, because they don't have to remember as much. Like a high-order compressor will have to remember a lot to compress well, but BWT is a sort of a mechanical transformation that lets a dumb entropy coder kind of perform pretty well. So as an example, we have some C++ source code. It's a pretty large file, but we compress it with both bzip2 and ppmd. So bzip2 is obviously faster, and ppmd beats it by like a margin of 2 kilobytes. But because bzip2 is faster, I would probably prefer that. All right, how many of you know Python? Right, so we'll make our own bzip2 in 5 lines of code. And the way we'll do that is to perform first the Burrows-Wheeler transform. As I said, we sort the string lexicographically in this line. And then we take the move to front transform, which is basically an algorithm that models the recency of a byte in a file. So if you have a repetition of bytes, then they will be encoded as zeros, because we use a queue. It's like a LRU cache with a fixed size or something, where we index into the LRU cache, and that's how we improve the compression. So after that, bzip2 actually uses something called run length encoding to collapse all those zeros together, and ones hopefully. But here I just decided to use Huffman. So Huffman coding is kind of annoying to implement. So I decided to just shell to zlibs Huffman coding implementation. We can also make a decoder that just requires reversing the steps and using inverse algorithms. So this is not a very efficient algorithm. It works. We can test it. That will be our test harness. And what are the results, right? So we have the same file called src.cpp. We compress it with a bunch of tools. We get like 23 kilobytes, 22 kilobytes. Here we have 26 kilobytes, which is not great. But given that it's 5 lines of code, I would think that it's fair. Yeah, so bzip2 is tens of thousands of lines of code for a reason. Here I have PS output for this program trying to decompress that set file. Right. So pack we've talked about earlier today. So notice how every single codec that we talked about works on the level of bytes, right? But there is some merit in looking at bits, right? Like how many of you have looked at an ASCII table? So an ASCII table is basically just an ordering of characters to assign them like byte values, right? But similar characters in the ASCII table are usually clustered together, right? So if you look at the high bits of a byte, then it turns out it's pretty easy to guess what the high bit's gonna be for instance, text, right? So this is why bitwise modeling is sometimes beneficial. It's generally somewhat beneficial. Yes. So what's the difference from ppm? Why is it so good, right? So instead of having the context as, the preceding few bytes, we now look at context as an arbitrarily complex function. So the context can come from a model, and it can be more or less anything. And instead of having the predictor, the single which you've seen in the previous slide, we're going to have a few predictors, right, that we're going to look at the file from many different angles. And based on that, we'll try to guess what is the final probability for the characters that we see. Right, so here we have 4 models. The 4 models guess zeros and ones, and we mix them together to get a final prediction. So a model is based on context hashes. So like, as I said before, the order n context as in ppm. We can also have occurrence of particular byte values. We can have a sparse model, indirect model, match model. PAC also has a dynamic Markov coding model, which is very funny in that it tries to build an automaton, like a DFA or NFA, you might know it from regexes. So it tries to guess something like that for the input and compress it based on that. Yes, so suppose that you wish to model text. As I said before, we can usually somewhat efficiently guess what the highest 4 bits are going to be, right? Because all the letters are clustered in the ASCII table. We can also make a guess that dots and commas are followed by spaces or new lines, right? That makes sense. And then Lepel's codec can't make use of that. There are a lot of possibilities. A lot of the models for PAC were actually implemented by people who are not mathematicians, right? It's not as difficult when you actually dive into the code. So here's a more concrete illustration, right? So models are implemented in code. So the models kind of look at the previous bytes to turn the previous bytes into some sort of a context, right? So I purposely don't say what the context is, because a context can be anything, right? It's just a number. And then the algorithm kind of guesses the correlation between the number and the prediction. So you might ask yourself a question. All right, I have a few models that look at the data in a few particular ways. So how do I combine all those predictions, right? So this is called mixing. There are a few mixing strategies. So Matt Mahoney started working with PAC many, many years ago, in fact, in the previous millennium. And his first few ideas for that were that you assign a fixed weight to a model, right? So when writing the model, you kind of guess how useful is it going to be when predicting the next bytes. But obviously, we can improve upon that, right? Like, this is not going to be very good for files that are not like the author thought they're going to be, right? So we sort of want to rank models. We want to, during compression, pick the most useful model, that is the model that's helping us the most. And PAC 4 to PAC 6 does it by basically checking what the model outputs, the actual probability, then checking the real probability of the next symbol. And based on that, we rank models higher or lower based on how accurate their precision was. So another obvious improvement is that we could use neural networks for that, right? So this is somewhat complicated. I mean, neural networks are all around us. Probably most of you have heard of ChatGPT or whatever. That's just glorified compression, right? But the actual theory behind neural networks is somewhat complicated. So we'll not talk about it too much, but if you're interested, you can ask a question. Right, so back on Earth. That was already too much math, I feel. So I made an attempt. Whether it's successful or not, you can judge by yourself. So as a preprocessing stage, we use some sort of a Lepel's derivative to find long matching strings in the file. And then we use the Burrows-Wheeler Transform and a context model. So the data is encoded using an order 0 model, right? So the compressor is really dumb, right? It looks at the previous, well, actually 1 or 2 bytes, and based on that makes the prediction, right? It also uses something called secondary symbol estimation, which is some sort of a check but verify method, right? So You can kind of trust the model to be right, but some people don't. I, for instance, don't. And we use something called secondary symbol estimation to kind of filter through the context further, right? So secondary symbol estimation always improves compression ratio, at least on paper, but it comes at a performance loss, which sometimes leads me to think of compression as a knob, right? You can turn it left to get better compression or turn it right to get faster compression. There are some people like Jarek Duda, for instance. He's a professor at some uni in Krakow. And he developed something called asymmetric numeral systems, which is used by Z standard, and it's one of the reasons why it's so awesome. So to quickly wrap up, BZ3 is not a very innovative tool, right? I mean, the idea that you can use, context models and BUT and, that particular kind of context model, like data compression nerds have known this for forever, basically, right? But the problem is that everyone who's not a data compression nerd usually doesn't care about it. So this is why we're stuck in the perpetual not invented here syndrome of having single-threaded gzip operating on 60 kilobyte blocks, right? Unfortunately. So I made the tool out of boredom during my high school exams 2 years ago. And I regret some things, definitely. I regret some decisions I took. And I plan to release a next minor version of the tool, or maybe major version, that is going to fix some problems I have with it. For instance, one of the issues was reported that when you try to compress a file, you should probably add an end of file marker, right? So that you can tell if the file has been compressed through, or that stream finished, or many other things. But I didn't add one, so that's on the list of things to fix. And my final thing is that maybe you should get interested in data compression, right? I mean, computer scientists think of both crypto and data compression as like black magic. They're not really very sexy topics. I mean, data compression is there's not much to be done here. There are some things to be done, but not much. But you should get interested in it anyway. So, the second part of the wrapping up. I'm currently working on a book that will explain data compression, and by virtue of data compression being somewhat tied to performance, right? I mean, if you want to compress, you want it to be fast. And if you want it to be fast, you want to use like some dirty low-level hacks to make it fast. So it's a very big project that I undertook, and I hope to finish it next year, maybe. But I don't have any experience with publishing. I mean, I haven't had any good opportunities to learn about it. So if you know something about publishing, you can always tell me. Thank you for attending my talk. Here you have my email in case you want to contact me. You also have my website with my blog if you want to read more about arcane things. And I would like to see if you have any questions.
We have a couple of questions.
Wow.
Yeah. Are there any meaningful differences in compression performance between popular CPU architectures or even manufacturers?
Yes. I mean, one of my friends has a Ryzen 9 5900X, I think. And I have the one with a 3 instead of a 5. So BZ3 is 4 times slower on my machine. I don't know why. That's probably a reason, but as with low-level code, you'll never know. Yeah, I mean, I was suspecting it will be cache, right? But you'll never know.
Can current improvements in LLM, given that LLMs are deterministic, can be used to improve compression ratio?
Well, there's a website that's hosted by Matt Mahoney, which is called a large text compression benchmark or something. You'll be able to find it if you Google for that, more or less. So if you look at the top algorithms on this list, you will see LSTMs, which is long short-term memory, which is one AI. Then you'll find the TensorFlow-based compressors. You'll probably find the LLMs there soon. They're pretty good at it, but very slow.
Does BZIP3 include backdoor, like, XZ style?
There might be some unintentional backdoors. Oh, sorry. There might be some unintentional backdoors, but I didn't plan it.
Can I contribute to make some backdoor?
Okay, that's a joke, all right? I know that's a joke, but I have a story about that actually. I mean,
You never know.
being an open source maintainer kind of sucks. I mean, it's kind of controversial to say it here, but it's made me want to quit open source like many, many times before. And if you follow the XZ drama, you will learn that Lasse Collin, which is the guy who makes LZMA, has been pressured by a bunch of people on the mailing list saying, why won't you focus on LZ for Java? Why won't you pass the maintainership to someone? The patches are on the mailing list for months. Why won't you merge them, right? So if I was him, I would also get depressed. But there were some cases where someone in the GitHub tickets has posted me a PNG of a medal for all of my work. I try to stay cool, so hopefully there will be no backdoors.
Are there any compressors utilizing GPUs?
Yes, of course. You can do, well, as you said before, LLMs, right? You can use LLM for compression, those run on GPUs. But also, the same person who is innovating BUT, the Ilya Grebnov person, has made an implementation of the Burrows-Wheeler Transform GPUs, right? It uses a lot of GPU memory, but it's somewhat viable, at least I think so.
Since both XZ, for example, and LZMA use LZMA algorithm, do their compression ratios differ, or is it just a different format?
Well, you also have LZIP, right? LZIP is the same thing. It's like LZMA, XZ, LZIP, probably even more. It's like 5 different formats that use the same algorithm under the bonnet. But no, they're generally a little different in that they apply preprocessing differently and use different flags under the bonnet. I think that the dictionary size in compression levels differs between LZMA and XZ. I personally don't see a reason for XZ to exist. Like, this is somewhat controversial as well, but like, we already have P7 zip, we already have LZMA. It's just a container format. And also I've been following a drama, which is very old, between LZIP and XZ, where the maintainer of LZIP wrote a very long document where he explains why a lot of compression formats are inadequate, because they are very prone to corruption. And he tries to convince us that his is the best, of course.
Is statistical compression used in lossy compression?
That's a fantastic question. I mean, I'm mostly familiar with lossless statistical compression, right? But the main issue I would see with lossless compression is that he wants to use it for something like, audio or video. It would kind of suck if it took too long to decompress, so they must use asymmetric formats. But for instance, you're familiar with the FLAC format, right? Well, the FLAC format is actually lossless. It uses polynomials to interpolate the sound wave and then cause the residuals. But MP3, for instance, uses Huffman coding. JPEG also uses Huffman coding. They could use arithmetic coding. I think JPEG XL, which is Google's not very beloved child, might also use some sort of a statistical, actually use some sort of a statistical model. A little known fact is that JPEG actually supports arithmetic coding, right? So there are a lot of JPEG files technically spec compliant that your computer won't read. But I feel that even if the standard allowed that, it wouldn't be very popular.
Were you able to gain any adoption of BZIP3?
That's a fantastic question as well. I mean, trying to convince people to use a new format is pretty difficult, right? I mean, the first sales pitch was that I'm gonna make a statistical compressor based on already known techniques, which will sort of improve the current scene of statistical compression. But the whole problem is that a lot of people don't want what I'm trying to sell to them, right? Not even sell, give away for free. Um, but I managed to get a MIME type from EANA. It's in many Linux distros, but some of the maintainers don't upgrade it very frequently. In general, yes, I've seen adoption. I've even received emails about it. Most notably, I received an email from a company which made me sign an NDA, and they gave me some data from a failing disk that happened to be compressed with BZIP3, wanted my help to restore it. I didn't expect that.
That's a nice story. What about lossy compression?
Uh, well, lossy compression is generally like a realm of audio and video, right? About lossy compression, again, statistical compression, I don't see that it would be very helpful with that topic. A lot of lossy compression actually comes from something called the psychovisual model. So the authors of lossy codecs basically try to guess what kind of thing can a human eye not percept or a human ear not percept. So most of the savings, for instance, in MP3s come from the fact that they use something called the discrete cosine transform, which is like FFT but sharper in a way. FFT will approximate to like a smooth waveform, and DCT gives you a sharp waveform. So they use this and then encode the coefficients, they manipulate them, hoping that nobody will be able to hear the difference. So if you've ever heard of MP3s compared to FLAC, you'll know that it's not true. But it's close enough and compressed really well, so why not? And also, a lesser known thing about PAC is that PAC can parse JPEG files, and sometimes even MP3 files, and recompress them better. But again, that's slow.
Is there algorithms that have the best compression ratio in, for example, ISO images and have the worst compression ratio in other tasks?
Yes, generally, I mean, codecs tend to be very domain specific, right? For instance, you could take a text file and you could cleverly encode it as an image, right? It's going to look like random pixels. That probably won't compress very well with any compression algorithm. But for instance, I've seen that BZIP3 is actually pretty good at compressing certain images and certain music files. So if you're familiar with Amiga trackers, right, or Commodore, I don't know if Commodore had those, but it's basically just a very simple music making tool which repeats the same sounds over and over again in patterns, right? So the reason why, for instance, FLAC won't compress it is that it expects a smooth waveform, right? Like a piano or a guitar, right? But the sound is completely synthetic, so BZIP3 can compress it better. That's a miracle or something.
Have you written any compressor in APL?
That's a surprising question. Well, I mean, APL is an array language, right? Like, have you ever used NumPy? If you use NumPy, you'll know that NumPy likes to process data in large chunks. But data compression doesn't really lend well to it, right? I mean, there's some things that you can do in large chunks, some things you can do in parallel, but you'll not accomplish as much as you would accomplish from, like, just serial processing, right? And APL is not that good at it.
These methods seem very similar to CPU's branch predictors or even value predictors. I wonder how these methods operate with very limited memory, like in CPU.
Well, a CPU, I've read a document a while ago that Intel's branch predictor has been fully reverse engineered. That's good news, but what we learned from this document is that it can remember branches, like history of branches up to 64 branches long, right? So notably, branch predictors are pretty good, but if you write fast code, they're not that good, and you still have to hint them sometimes. But most importantly, if you use fast code, right, then if you write fast code, then all of your code is kind of condensed in a small chunk, right? Otherwise, you're going to suffer from other issues like I-cache bloat or something, right? So if you compress, if you want to predict branches, your algorithm will be the most important on like very tight loops, which I imagine don't need that much memory.
And that was the final question. Thank you very much. Applause.